So good afternoon, everybody. My name is Raphael Meyer. I live and work in Switzerland in a mid-sized company called BBV. We're a contracting and consulting company, basically based in Switzerland with offices, a few offices around the world, but we're focusing on German-speaking Swiss and German customers. So that much about myself. Or maybe my I'm my customers I have are mostly embedded or industrial companies. So it always has to do with machines or kind of hardware, and therefore I mostly use C++ and are in some kind of embedded field, whatever that means. So let's get started. So the title of my talk is Error Handling Revisited. And what do you mean with error? So in software, we could really talk a lot about errors. There are various kinds of error happening everywhere or could happen. So, but in this talk, I only want to focus on one specific kind of error. So if we have software and the software should do, or we want the software to do something at least a little bit interesting, then we have to deal with the outer world or the world outside of the software. So we maybe have a user interface that we can interact with the users, or we have sensors or actors that we can engage from the software, or we maybe have a database, or we want to send data to the web or wherever. So, and if we are kind of interacting with this outside world, then there are things that could go wrong. And that's specific the kind of error I want to talk about today. So how should we handle that if we have to kind of deal with the outside world, but things can go wrong? How should we deal with that kind of error? And I will just introduce a small example. Let's say I have a nice plant in my living room, but I'm really bad at watering the plant, so they always die. So I want to come up with some kind of automated plant watering system. For that, I have some kind of a microcontroller board. I have a moisture sensor to find out how much moisture is still left in the earth of this plant. I have a temperature sensor for the ambient temperatures because maybe the plant needs a little bit more water in hot summer than in cold winter. And I have a pump to actually get some water to the plant. So if I would code up something like that in C++, it might look a little bit like that. So just for examples, I have a few signatures of this moisture sensor reading out functions and the pump functions, and the other functions are more or less the same like that. So and then we have this function water in the watering system to actually do the watering of the plant. So we're reading out the moisture from this moisture sensor, we're reading out the temperature from the temperature sensor, and then out of the moisture and the temperature value, we calculate the amount of water we actually want to pump to the plant, and then we do the pump action, and then in the end, for that, if you want to do some logging or whatever, we return the amount of water that we have given to the plant from this function. So, but now, what if something goes wrong? What if the pump is stuck or there is some cabling issue and the temperature sensor can't be read out? What should we do then? So there are different patterns of how we could manage or handle this kind of errors if we get some error from the various actors and sensors. So one pattern that I often encounter is that we have these nested ifs. So I try to read out the moisture sensor, and if this works out, then I try to read out the temperature sensor, and so on and so on. And the more actions or I have to take in this sequence to get something done, the deeper the nesting. So this doesn't really scale. It does not look so nice. So it's maybe okay for 2 or 3 actions, but when it gets longer, it gets deeper and deeper and deeper. What I also don't like that much is now I had to introduce something to report that there is something going wrong. Now in this case, I just return a bool saying, okay, if it's true, then it was okay. If it is false, then something went wrong. And now the actual value I'm interested in, for example, the moisture value out of the moisture sensor, I had to convert that to an output parameter. Now, there are various kind of options how you could do output parameters. Here, I just put in, for simplicity, a reference, but it could also be a pointer, it could be a smart pointer, it could be something else. But the problem is, if I return false, what happens to my moisture? So what can I assume about this value? Is there something going on or not? If it's a pointer, then it's even worse. Even I need to have some documentation. Do I have to provide already the object, or is it created? And what state is it in if I get a false back? Another pattern that I often see is the early return. So it's basically the same thing as before, but just instead of nesting, we're doing an action, checking it. If it went wrong, we return false. So it's basically the same. It's just instead of nesting, we have these early returns. And then the third pattern I often encounter are exceptions, or maybe I encounter them not that often, because in my experience, I often had kind of projects where exceptions were forbidden to use. I often had the impression the reason why they said we're not using exceptions were more arcane esoterica instead of facts. Maybe they should have attended yesterday's workshop, I think it was by Ben Sachs, who was talking about exceptions. But one interesting thing that or a discussion I had with a colleague of mine who's a .NET developer. He's mostly doing C#, but he's very much into F#. And he said, I don't like exception because they're kind of like a go-to. They're like an extended go-to, a go-to on steroids. And it breaks the flow, so it makes readability hard because you have to kind of catch exceptions, but it's not so clear where they're coming from. They could be jumping from quite deep down. That was something interesting. And I wanted to learn a little bit more why he was reasoning like that. And that led me to, some time ago, start reading a book about Haskell. So this is it's also called the Elephant book in contrast to the Dragon book. It's quite a fun read. And I started to read it. And when I was reading it, I saw that if we're doing the example before, if we were going to do this in Haskell, it might look like that. And what is surprising is that this code, even if you don't know Haskell, I suppose not a lot of you know Haskell, or are there some Haskellers here? Even if you don't know Haskell, the code is not so hard to understand. So we have this read moisture function. It returns some kind. It's not moisture. It returns maybe moisture, whatever that means. But we get this moisture with this kind of arrow to the left into a variable called moisture. We do the same with the temperature. Then we call this calculate amount, and there we get out the amount. So it's not so hard to read. But of course, the C++ code was also not hard to read because apparently there is no error handling there. So, I mean, it would get much more complicated if you also add the error handling here. But the error handling is already there. That's the surprising thing. So, but who saw some error handling? I didn't see any error handling. So the error handling, it's there and it's explicit. Because if as a Haskeller we read the signature of this watering function, you see that the water plant function, it doesn't return a volume, it returns a maybe volume, which means you maybe will get the volume back, but maybe you don't. And then this is kind of the first thing, that the maybe says something could go wrong. And now the second part is there is this do, which for us as C++ programmers, it maybe look a bit, there's just a do there. No, the do is something completely different in Haskell. And in this context, it kind of is an indicator to tell us, but I'll take care of it. So it's been taken care of that we handle it when something goes wrong. And then there are a few small details in Haskell. So like the type system, lazy evaluation, and whatever. It's just that makes kind of this code that simple as it is. So let's have a look at the maybe. And for that, we're going to see some code. So let's assume we make up just a very, very simple example. So I want to have a function to cut something in half. Say I have a few coins of euros or kroner or whatever, and I want to cut them in half. So I say I have this half function, which takes an integer and it returns an integer. So to implement that, it should be quite easy. I just say, okay, let's use integer division and cut it in half. So let's try it out. What is half of 4? Half of 4 is 2. Half of 8 is 4. And half of 7 is 3. Because we cannot divide one coin, so it's hard to cut the coin in two halves, except you have the tools for that. But maybe in some countries it's even illegal to cut coins. At least I think in Switzerland it is. Yeah, so we get back 3, and like 1 is lost. Now, what we also can do is we could try to, what happens if I try to, oh, it looked strange, so therefore, okay. We could also kind of chain, we could say, okay, take half of 16, and then I want to cut the result of that again. So I say half of 16, which is 4, and I can do that again, and then take half of 16 is 2. And it also kind of does something with 18, which would be 9, and half of 9 would be 4, and the half of 4 would be 2. So that's what we have seen in the live coding. But now we said, okay, it doesn't really make sense, or we have this problem that if we have odd number of coins and we want to divide them into two halves, it kind of doesn't fit. So we're going to say, we want to say we are only going to have even numbers of coins. So if you have an odd number, we will say, no, this is an error. You can't have an odd number. So we're introducing this maybe. So what is maybe in Haskell? Maybe is something like just it's a data type. You can imagine it something like a struct or a class or something similar. And it has some special kind of, it's like a template type. We have this data maybe A. So A is like a template type. It would be maybe like template type name A, struct maybe. And now what can this maybe be? It can be either a nothing or it can be a just A. So that's very interesting. So if you have an instance of a maybe, it can be a nothing and it doesn't have this type it had. Or it can be just A, which is just the value. So if you have a maybe of an int, then it can be nothing, or it can be just an int saying it's a just holding an integer value. So how does that look? So we're going to change our implementation and say, okay, the half function takes an integer and it will return a maybe integer. And then we also, of course, have to change the implementation. So it did not change that much yet. I just said, okay, I have kind of I added something saying, okay, half n is in the case of if n is even, then I still return kind integer division by 2 and pack it in a just. And then if it's odd, saying otherwise, I will return nothing. And we should type it correctly. Okay. So what's happening now? So if I say half of 4, I don't get just the 2 back, I get back just 2. So this result 2 is packed in a just 2. What happens if I say half of 7? So I get nothing back. And now, what we did before, say, okay, I want to take, that doesn't work. We take half of 8, saying, okay, I want half of 8, which will be 4, and then half of 4 will be 2. But that doesn't work because our half function doesn't return an integer, it returns a maybe integer, but the half function takes an integer. So we cannot chain these calls anymore. So we would have to kind of maybe take as an input the maybe integer, or before we call it the second time, we have to look it up and see if it's a nothing or is there a just value in there, and then we have to unwrap the value and pass it in there. And maybe go back to the slides. That's what we have seen. So because this is such a common problem, or this is such common in Haskell, not really a problem, but occurring a lot in Haskell, they have this thing called bind operator. It looks like this right shift equal operator. It's called operator bind or bind function or bind operator. And what is that? So this operator is defined as a function that takes a MA. MA means it's like a template type. It's like a template type M, and the template type M itself is another template type. So it's a template. So meaning, for example, it could be the M could be a maybe and the A could be an integer. It could be a maybe integer. And then as a second argument, it takes a function that takes an A and creates an MB out of that A. So meaning, for example, it could take an integer and then return a maybe float from that integer, or another maybe int. And then the final result will be a MB. So as we have seen before, we had this problem. We have then function taking an integer and returning a maybe integer, but the result we wanted to put in that function was a maybe integer, not an integer. And now this operator looks like it's really going to help us, because we can now put there an maybe integer. We have this function from an integer to a maybe integer and getting a maybe integer back. So how is this operator implemented for the type maybe? It's a really simple implementation. So all this implementation says is if I have a just x and I give that just x to the bind operator, and I have this function k, which is the function from a to mb, then I just apply the x which is in that just x to the function k. So I call function k with x as a parameter. And if the parameter for the bind operator, first one, is a nothing, then I don't care what the function is, I just ignore it and return nothing again. So it's a really simple implementation. I don't need to. So will that help us? So I said half of 8 is just 4. Now if I say half of 8 and I use the bind operator and call half again, I get back just 2. Because that bind operator looked at the result of half of 8, so it's a just, and then just pegged out the 4 and gave it to the next half function. So what happens if I say half of 18? That is just 9. So I'm going to stuff that again in another half call, and then I get back nothing because we know that half of 9 is nothing. And what happens if I do it again? Will I get some runtime error? No, of course not. I just get another nothing because the second bind operator got as an input a nothing and said, okay, if it's nothing, I don't care what the half function does. I will just return nothing again. So that's what we've seen there. And now, because this bind operator is also something very common, there is something called the do notation. What is the do notation? We've seen the do before. I said the do is kind of indicator that there will be some error handling happening. If I now rewrite the example from before with my plant watering system, with the bind operator, I get this construct that I say, okay, I read out my moisture sensor, and then this result of read out the moisture sensor is maybe moisture. So maybe there's a moisture, maybe there is nothing there, or maybe I have the moisture value. Then I use the bind operator, and the second argument to the bind operator is a function. So here it is a lambda. So this backslash is introducing a lambda, and the lambda takes up the rest of the code here, all these remaining 3 lines. And the lambda has one argument, which I call moisture. And then after this arrow operator is the implementation of the lambda. So the function that we're giving to this bind operator. So what does this function do? It will read out the temperature sensor. Then the result of the temperature sensor is maybe a temperature. We're again passing that to the bind operator together with another function. And this other function is again a lambda, which takes a variable called temperature, that will be our temperature value, and then it will calculate amount, which will give the maybe amount or maybe volume as a result. There maybe is an amount of water in there, or maybe there's nothing. And this result again, we're going to give to the bind operator together with a lambda, which then actually does the pump action. And then there is kind of a special, it looks like the bind operator but missing the equal sign. It's basically the same thing, it's just because the pump action has no return value. We're seeing it in the signature instead of maybe a type, there is maybe this bracket or square brackets or parentheses. And this just means a void type, so it has a non-type. So therefore there is no equal sign because there is no type return, but it's basically the same thing as the bind operator. And now because this is such a common pattern, there is this do notation. So now we have this, in the bottom part, we have this water plant is do, and then instead of kind of read moisture and then the bind operator, we have read moisture with this left arrow to variable called moisture. And this do notation, it's just kind of syntactic sugar. In compiling Haskell, this is just something that kind in front of compiling process, this will just be converted what it's up there. So with these nested lambdas. So it's kind of just helping us to unwrap this nested lambda to something that's more readable. And if we would kind of try out making up a main, which says, okay, I'm really going to call the water plant function. And if it went okay, I will print out the amount of water that I gave to the plant. If not, I will print out some error message. It could look like that or like this. So also the bind operator is something that it's so crucial to Haskell. It's not only the maybe that implements this operator. There are a lot of other and also kind of surprising data types, like for example, these square brackets mean a list. The list also implements the bind operator. You can do very interesting stuff with that, or it can help you to rethink what a list is if you're applying that. Some other type besides the maybe, which is also very interesting, is either. So what is a either? Either is a data type, which is also kind of like a template type, that has two template or generic types, the A and the B. And the either can have one of two values. It can be either a left A or it could be a right B. So if I have a either of integer float, it could be either a left integer or a right float. And then there is a convention which kind of historically grew, or I don't really know how it happened, but it said that right, because right is a right value, or right is a value, and if it is a left, it is an error. So this either type is often used to not say it is either A or B, or to say either it is a value or it was an error. And then if it's an error, it's in the left. And also this either also implements this bind operator. So how does that look? So it's also the implementation of the bind operator is quite simple. It just says, okay, if there is a left L, then I don't care what the function is that you're passing me. I will just return left L again. But if there is a right R, I take this function called K, and then I just call function K with the value of what's in the R, in the right, the value R. Also very simple. Just saying error stays an error. If I have a value, I'm going to do something with it. So if I rewrite my water plant function to use either instead of maybe, that for example, I can give back a more sophisticated error what was really happening. And also all these functions I use in my water plant function will return either error and then whatever value. Then my function looks like that. So there are just a few changes. So the signatures have changed from maybe moisture or from maybe null type in the pump to either error null type, or the read moisture to either error moisture. And also the water plant is just instead of maybe volume, it's changed to either error or volume. And the code itself didn't change at all, because it's still using the bind operator and still using the do notation, which is just syntactic sugar for nesting the bind operators. So I didn't have to change anything in the code itself. So it's very similar. And if I was also going to create a little main function, calling the water plant function and then printing out the results of that, if it's going okay, I will get back this volume. If I have an error, for example, in the temperature sensor readout, I maybe get back the error message that was really coming from the temperature sensor, or the function calling trying to read out the temperature sensor. Now let's take a little detour and dive a little bit into Rust. In Rust, there is a type called option. And I find it very interesting. It's not like a class or something. It's a enumeration. It's a enum type option. And it seems to be that enums in Rust, they can be generic, like templates. So because there is this T, which is a generic type T. So the enum is not is very different from C++ enums. It's more like a standard variant. We will see that again after. And this enum type can be a none or some T, meaning the none has no value, it's just the enum type, it's the enum value none. Or if it's a sum, then it can hold a value of type T, or it holds a value of type T. And this is very similar to the maybe, that could be a nothing or just some value. And here it's just the just is called some and the nothing is called none. But it's quite the same type. And then there is another interesting type called result, which has two generic types, a T and a E. And this result type can be either a OK, holding a value of type T, or it can be an error, holding the error E of type E. Now, if I would rewrite or try to implement my watering plant function in Rust, it might look something like that. And so the water plant function, it now returns a result, which could be the volume, what we really gave to the plant, or it could be a string representing an error. And if I'm going to call that, I will first try to read out the moisture sensor. And then I try to assign this result to a variable called moisture with let moistures. And then there is this match operator. So what does match do? So match will just take the result of this read moisture function call and then look up. It's like a switch on this enumeration and then see, was it the OK or was it an error? If it was an OK holding value M, then this match operation will return to the assignment operation the value M. So I'm kind of unwrapping the M in the OK and just returning that for assignment to the moisture. But what happens if there was an error in the result of read moistures? So if there is an error E there, I literally call return error E to just return from the function. So this is not assigned to moisture, but this return will return from function water plant. So it's an early abort to return this error. And then I do the same for reading out the temperature, calculating the amount, and then in the end, really activate the pump to pump the water to the plant. So there is a little bit of Rust specifics that the result of the pump, I don't assign it to anything, and there is a missing semicolon, which is not a missing semicolon, that's just a Rust syntax to say the last statement in a function that is not closed by a semicolon is the return value. So the function returns the result of match pump, which could then be either this OK, and then I return the OK amount, so the amount we pumped, or if it was an error, we just return that error. Now, there is a lot of repetition there. So we see that like this match operator, what's written in the match operator, what really varies is kind of on what value do we match? So it's either read moisture or read temperature or calculate amount or pump. But what's then in there is always the same thing. We could just replace these M, T's or V's with an X and then they all would be the same. It would just be OK, X, return X, error E, then return error E. And because that's a lot of repetition and very tedious, they introduced something in Rust called the, I don't know how it's really called, but it's a question mark operator. I don't know if it has a special name. It's a little bit easy to oversee, but if you look at it, you see that the read moisture in the end has a question mark. Read moisture? Did we really read out moisture? Okay, maybe. So, and what this question mark operator does is exactly what we've seen before. It's exactly just syntactic sugar, you could say, for this here. So if the read moistures returns an error, then it will just return an error from the whole function, so from the water plant function. And if the read moisture returned really a result, it is assigned to this moisture variable. And if you would try to make up a little main function and try to really run it, we see there is another match on the whole water plant function there and printing out either an error or saying, okay, we've given that much water to the plant, which will then, if it's successful, given some water to the plant, or we maybe see some specific temperature sensor error. So, but now back to C++. So in C++ 17, we got standard optional. Maybe standard optional is, maybe let's have a look at the code. So standard optional is like the maybe. And if we reroute our C++ code with standard optional, I say, okay, now the reading out the moisture sensor returns an optional moisture, saying it maybe returns moisture and maybe there is no result in there in C++ called standard null opt. And then I also have the pump function, where I just for kind of consistency, I also said it was going to return an optional, but it doesn't really have a return type. It was more like it returns nothing pump. So I have this standard monostate, which was actually introduced for another reason, I think, but I can misuse it or borrow it as the null type. And then the watering system water function, it will return an optional volume. So maybe it will return the volume of what was of the water that was given to the plant, or maybe it won't return nothing if there is an error. And as you can see now, when I compare it to kind of one of the first examples with the early returns, it looks like the same as the early returns, where I had, instead of optional, I returned a bool, and then the value that I wanted to return was an output parameter. It's like the same thing, except I could say the standard optional is nothing more than kind of a Boolean flag to say it holds a value or not, and the value itself. So semantically, there is not a lot of difference there. But if I compare that to the other one, it's kind of more descriptive. It really says, okay, you will get the volume back if everything went right, but if not, you won't get back anything. You don't have to take care of if I did something to your output parameter, because there is no output parameter. So it's more descriptive to know what this function actually does. And then there is the standard variant. Standard variant is a very interesting type, also added to C++ in C++ 17. It's basically a type-safe union, to say simplified, in a simplified manner. And we can use it to implement something like the Haskell either or the Rust result. Now, if I'm going to rewrite my code to use a standard variant, where I say, okay, I have for the watering system water function, I have a standard variant volume error, saying it will either return a volume or an error, and then having all my functions that I use in there to say, okay, for example, reading out the moisture sensor returns a standard variant of moisture error, saying it either returns moisture or an error, and the same for the pump. Also change that to a standard variant. Then it's also the code, kind of the signatures of the function is very descriptive. I don't need a lot of explanation to kind of find out what could the water function do or what do I get back. So because it says, okay, get the value or an error back, and there is no kind of strange state if it returns a bool or some other kind of error code, and you have output parameters, and they're not knowing what output parameters got changed or got they changed or what can I do with them after that if I get false back. So it's quite descriptive. But on the contrast, the implementation to handle in there, it got very verbose. So I'm reading out the moisture sensor. I get back the standard variant. I have to kind of look up, is there an error in there? Which is, for example, here I use standard get if, which returns a pointer, which is a null pointer if it is not an error, and it's not a null pointer if it is an error, and I can check on this null pointer, and then if it is an error, I return this error. So the code is not that readable anymore. It's not difficult to read, but there is a lot of, you have a lot of verbosity, or you have to type a lot. There's a lot of boilerplate, which kind of hides the interesting parts, and there are a lot of details. So that doesn't make it that nice. So we could try something else. We could say, okay, standard variant has a nice friend called standard visit. They're often seen together, and we could try to implement it with standard visit. Now, to use standard visit is I can give it something like a standard variant, and it's implementing the visitor pattern that depending on what variant it is, it will do something else for each of these variants. Now, to use this standard variant nicely together with lambdas, so I want to pass this standard visit a bunch of lambdas, one for each variant that is possible. I need a few helpers. And this is something you maybe can take out of this talk. You maybe don't have to memorize it by heart. I can't either. But you should only know that if you're going to cppreference.com and look up the documentation for standard visit, you find an example with this helper. So what this helper does is it helps to build up a type out of the lambdas to have an operator to call the type, to make it callable for each of the lambda, and then helping also the compiler or the template, the type deduction, to really find out what lambda matches with what. So I think in C++10 it should get a little bit more simplified. I don't know. The second part is user-guided type deduction. I think we don't need it anymore, but I'm not sure about that. But I heard something that it should get a little bit easier. And then I added a second helper, which is I just do some type aliases. So I say, okay, when I have a standard variant that has type T and then an error, I just call that result, and then I even make an alias for a special result, the result of the volume, which I call amount. So amount is basically an alias for standard variant volume error. So in the next slide, if you see somewhere an amount, just imagine there would be standard variant volume error standing there. If you see the slide, maybe you know why I made this alias, because it wouldn't fit anymore on the slide, because there is a lot of amount there. It's maybe not that visible because there's so much code. So the standard visit didn't really help in that case anymore. To be fair with standard variant and standard visit, there are a lot of interesting design patterns to use them, but here it didn't really help. But they have their use cases that are really good. Maybe to explain a little bit what's going on here. So we start with reading out the moisture sensor and assigning that to variable moisture. And then we're going to call the standard visit with this moisture value, and as the first parameter of standard visit, passing it that kind of these lambdas, that I want to use a lambda for each variant I have on my result type. So one for the error and one for the moisture type with this overloaded helper we saw before. So now if the moisture holds an error, we're just going to return that same error E packed again in an amount. And if it was a moisture value, then we're going to call we're doing our lambda, we're going to call or read out the temperature sensor and get the temperature value back maybe. And we're also calling standard visit on this temperature value. And then the same is happening again. If it's an error, we just return the error. If it's really a temperature sensor, we have this other lambda, which then is going to calculate the amount, how much to pump, and then it's visiting this amount value again. And if it's an error, it's an error. And if there is an amount in there, we're going to use the pump to pump the water to the plant and so on until we end up kind of having done all our work. And if we had an error with pumping, then it's still an error. And if it was okay, we will return the amount. Now, as a small optimization, what we could do, we could take out these local variables we had, and I could just directly call them in the standard visit calls. Now, what we gained is that we have all this interesting part, like really the code that does the interesting parts, like reading out the sensor, activating the pump, and so on, is in one place. There is no boilerplate around or between them, but they're in the wrong way around, and they're hard to spot because they're still kind of at the bottom of some tedious code. So that didn't help that much. If you would write a small main function trying to exercise that, it's not that surprising. Here the standard visit looks a little bit nicer because we don't have that much of nesting, and this is maybe a better use case if there is no nesting. It's just we get something back where we have two options and we want to look what we do with option A or B. And yeah, it's the same thing. Either it worked out, so it will print out I gave that amount of water, or we see what kind of error that happened. Now, what we could try to do, we could try to build up our own result type as we have seen in Rust. Now, if I write something like that, I will just reuse the variant. There is still, as a basic type to store really the value, I still use the standard variant. And in this class, I just write a few helpers, like a function returning the error value or the OK value, and I just forward it to standard get. So it's basically just forwarding or using something in with another name, changing a little bit the signature. I have, for example, a check function to check is it an error or is it not. And the most complicated thing here is just this constructor, which is just a nice little helper that tells me that I will just, this is a constructor taking some type T, and it will just accept anything that I can convert to my special standard variant holding the error or the value. So this is just convenience functions to say, so instead that I really have to make up my result type, I can just assign, if I, for example, have a string and a float, I can just assign the float, and then it will assign the float to the error type, or vice versa. And then there I have two functions just to kind of the maker functions to create something. I don't use it in the next example. It's just for maybe we want to use that we have these make functions where you can say make OK or make error, and then we'll get back a result withholding that value. That might be convenient. but we don't have to use it here. Maybe use it then in the implementation of reading out the moisture sensor like that. So if I now rewrite my code with my homegrown result type, what's happening now is it's still basically the same as when we use the plain variant, but a lot of this verbose boilerplate code has gone away. It's much more readable. So it's quite surprising that we still have to check with the if and do this and return the error if it is an error, but there is not so much boilerplate going on to find that out. So that helped a lot. So this code, I think, is much more readable, and the signatures are still they're very descriptive. And if you're going to write a small main, it's basically the same. It's not that surprising. Now, as an experiment, we could say, okay, why not try to implement the bind operator from Haskell in C++? Now, for my result type, this is a very naive implementation. If you want to really kind of have it behave more like the bind operator, especially the template argument func, which takes the function, there is no restriction there on that it should behave as it should behave. I could also pass something else. It just has to be callable on the value of the OK value. But just for simplicity, let's stand it like that. And if you look at this implementation of this bind operator, it is very simple. It's just checking, is it an error? Yes, it is an error. Okay, return the same error. If it is OK value, I take this function f and just call the function f on the OK value and return that. That's basically the same thing as we've seen in Haskell. It's quite simple. Now, if I rewrite my C++ code to that, it looks like that. That's very surprising, kind of. Oh, it looks very short. It is somehow readable, maybe not for the C++ programmer, but for the Haskell programmer. So if maybe Haskell's programmers are forced to write C++ code, it might end up that they start writing code like that. Maybe not so good for the C++ program, because I think if you see something like that, will be, what the heck is that doing? I don't understand. But because we have seen the Haskell code before, we kind of know what it is doing. And very interesting, it really, except for there are a lot more return statements in C++, we have kind of do some nasty thing with capturing there, and there is some autos, but except from that, the code looks very, very similar or almost equal. And now, if you remember from before, we had in Haskell this do notation, which makes everything even more readable. So what if we could kind of implement something like the do notation in C++? But to be honest, I have no clue how to do that. So I'm sure it involves some sorcery and maybe some unicorns, but I have not yet an idea how to do that. That it does. I know maybe it can be done, but I think then it will not be readable at all. So the goal is to have a readable do notation in C++. So what did I learn from that? So either I'm going to look for a new job as a Haskell programmer, that I don't have to mess anymore with all this C++ stuff, or maybe I could spend some more time learning some more C++ template meta programming, which will maybe help me with implementing the do notation or something else. So to wrap up, so what I would like you to give out from this talk is that you start using value types. It was not so explicit in the talk, but it basically is all based on using value types to make the code more expressive. So instead of having output parameters, or instead of having a class which has 3 booleans, and depending on these booleans, the other members will have a valid value in there or not, that you start kind of trying to make things more expressive, that it communicates more clearly its intent. And the other thing is, what surprised me a little bit is that it, I can't say it was not so hard to write this result wrapper, but it is not really that hard to write them if you start to think about it and not try to re-implement something like a standard variant, because for example the constructor of standard variant is really sophisticated because of the restrictions or constraint it has on it, but you don't have to do it. You can, in my example, I can just say, okay, I want to have the same functionality, but I'm using it. So I just have to write a template to say, okay, I borrow this constructor if it is, in my case, if it was convertible. So, and I think with concepts, maybe even I had to use some Sphinx there. With concept, it should even be easier to say, okay, I will just borrow the same concept and I don't have to re-implement it. And so I want to say, don't be afraid to write such type if they reduce verbosity. In the case of kind of compare my result implementation to use raw standard variants, the improvement was quite big in my opinion. And as a last kind of advice, I want to tell you to keep your eyes open to discover the functional gems that are in your language or inspired your language. And especially the last few years, there was a lot of rediscovering going on from old functional concepts, and they start dribbling into the different languages. Or even like in the case of Rust, if you I don't really know a lot of Rust, but what I've seen, and I also don't know that much of Haskell, but when I looked at Rust, after I knew some Haskell, I always had a lot of these aha effects and say, oh, that looks like they borrowed something from Haskell. And then also maybe start learning a functional language as kind of your, I call it kind of recreational puzzling, to just learn some new perspective. Also to spot all these functional gems that are hidden in the language we use daily, but also kind of to gain a new perspective on to look at things. So that's all from my side. Thank you.